There is a wall in the sky. You cannot see it. No telescope will ever photograph its surface. No probe will ever touch its edge. And yet it is already there, closing in around every civilization that has ever looked up and wondered how far the universe goes. We like to imagine exploration as a matter of will, that given enough time, enough fuel, enough patience, any distance can eventually be crossed. That is the story we tell ourselves in every film about starships and colonies among the stars. It is a beautiful story. It is also, according to the physics we now understand, false. Because the universe is not a static ocean waiting for us to build a bigger boat. It is an ocean whose far shores are pulling away from us and pulling away faster with every passing year. Somewhere out there, right now, while you listen to this sentence, galaxies that our grandparents could once have theoretically reached are slipping past a line they can never cross back over. They are not moving away from us in the way a car drives away down a road. Space itself is stretching between us and them, manufacturing distance out of nothing, and it is doing so at a rate that eventually outpaces the fastest signal we could ever send. Light itself, the ultimate messenger, the fastest thing that exists, is losing the race. This is the story of the edge of everything we will ever be allowed to touch, not the edge of the universe. That word implies a boundary we might one day stand at and look beyond. This is something colder and stranger, a horizon of permanent exile, expanding invisibly through the dark, quietly erasing galaxies from our future the way a tide erases footprints from a beach, except the tide never turns back and the footprints never return. Astronomers gave this problem a modest, almost bureaucratic name, the cosmological event horizon. It sounds like paperwork. It is, in truth, one of the bleakest conclusions in the entire history of science. It tells us that no matter how advanced our civilization becomes, no matter how many centuries or millennia pass, no matter what technology our descendants invent, there will always be a boundary past which nothing, no light, no radio wave, no signal of any kind, can ever reach us again. And that boundary is not fixed. It is shrinking. Every year, it swallows a little more of the reachable universe, folding galaxies into a silence from which they will never again speak to us. We built our entire understanding of the cosmos, assuming that with patience, distance was negotiable. Every equation of relativity, every model of cause and effect, rests on the assumption that if you wait long enough, a signal can cross any gap. That assumption has just been quietly retired. Somewhere in the data of the last few decades, cosmologists confirm that we do not live in a universe of open roads. We live on an island, and the shores of that island are retreating. Let us sit inside that word for a moment. Island. It sounds almost cozy, doesn't it? An island, a shelter, a defined and knowable place. But consider what kind of island this actually is. Imagine standing on a beach and watching the water pull back, not toward a tide, but into an accelerating retreat that never reverses. Imagine that every plank of wood you gather to build a raft takes years to cut and assemble, while the ocean between you and the next island widens by kilometers in that same span of time. No matter how fast you build, the distance you must cross grows faster than your capacity to cross it. That is not a metaphor for effort. That is a mathematical certainty for most of the observable universe. And it is the terrifying truth hiding beneath the phrase, "the universe is expanding." We are not simply isolated by distance. We are isolated by a widening moat that eats every bridge we could ever construct. And here is the detail that should genuinely unsettle you. This isolation is not something that will happen someday. In some distant era we can safely file away as not our problem. It is happening right now, this very moment, as invisibly and silently as rust spreading through a hidden beam. Galaxies are crossing that horizon today. Some may have crossed it while you were listening to this very sentence. We simply have no way of knowing exactly which ones, or precisely when, because the effect is gradual, cumulative, and utterly without ceremony. There is no flash of light, no final broadcast, no dramatic farewell. There is only a slow fading of signal, an inexorable redshift stretching every photon until it grows too weak, too stretched, too red to ever arrive. This is the crash of an assumption that ran quietly under everything humanity has ever imagined about its cosmic destiny. The assumption that space, however big, was fundamentally ours to eventually explore, given enough centuries. The mathematics of an accelerating universe took that assumption and, without asking permission, tore it out of the textbook. So we begin here, at this fracture, not with wonder for its own sake, but with humility, because what we are about to describe is the shape of a cage we did not know we were born inside. Let's talk about scale, because numbers alone will not save you from what is coming. Numbers are too polite. They sit quietly on a page and let your mind skip past them. What we need instead is a feeling, the physical, almost nauseating sensation of smallness that any honest confrontation with cosmic distance eventually produces. Picture the local group the way you might picture a small town. In this town live a handful of prominent households. Our own galaxy, the Milky Way, our largest neighbor, Andromeda, a smaller cousin called Triangulum, and dozens of dwarf galaxies scattered like modest cottages around the main houses, satellites bound gravitationally into this shared little neighborhood. This town, by cosmic standards, is genuinely small, a pocket of gravity strong enough to bind these galaxies to each other permanently, resisting even the relentless stretching of space itself. Within this town, distances are negotiable. Andromeda, in fact, is not fleeing from us at all. It is falling toward us, drawn by gravity so strong that it overcomes the expansion of space entirely, and in a few billion years, it will merge with our own galaxy into a single larger structure. But step outside the boundary of that town, and everything changes. Beyond the edge of the local group lies what cosmologists sometimes call the local supercluster, and beyond that, cluster after cluster after cluster, an ocean of galactic cities stretching in every direction, as far as any instrument can measure. And every single one of those cities beyond our town, without exception, is retreating from us. Not because they are moving through space in the traditional sense. Think of a raisin in a rising loaf of bread. As the dough expands, every raisin moves away from every other raisin, not because the raisins themselves are crawling through the dough, but because the dough between them is stretching. Replace dough with space itself and raisins with galaxies, and you have the honest picture of what is happening around us at every moment. Now here is where scale becomes something closer to horror. The rate at which this stretching happens is described by a number cosmologists call the Hubble constant, roughly 70 kilometers per second for every megaparsec of distance. That number alone means nothing to your gut. So let's translate it into something your body can actually feel. Imagine you are holding a rope 1 kilometer long stretched out in a straight line before you. Now imagine that every single point along the entire length of that rope is quietly, continuously growing longer, stretching outward on its own, with no force pulling from either end. The rope itself is manufacturing new length internally, everywhere at once. The farther along the rope you look, the faster that particular section is stretching away from you, purely because there is more rope between you and it, and every centimeter of that rope is expanding at the same tiny rate. Multiply that effect across billions of light years, and eventually, far enough away, the rate of stretching between 2 points exceeds the speed of light itself. This is not science fiction. This is not a hypothetical loophole. Nothing is moving through space faster than light. Space itself is simply expanding fast enough that the distance between 2 points grows faster than light can cross it. It is the difference between a runner sprinting down a track and the track itself lengthening beneath the runner's feet faster than they can run. The runner never technically breaks any speed limit. The runner simply never arrives. Consider your own body for a moment, as ridiculous as that sounds. If you were to shrink the entire observable universe down to the size of a single grain of sand, our local group, the Milky Way, Andromeda, Triangulum, all of it, would occupy a space so unimaginably tiny within that grain that no microscope built by human hands could resolve it. And yet within that microscopic pocket, we consider ourselves capable of grand cosmic ambition, dreaming of colonizing other star systems, of one day reaching other galaxies, of becoming a spacefaring civilization in the fullest sense of the word. The uncomfortable truth is this: even if we could travel at the speed of light itself, a physical impossibility for any object with mass, the vast majority of galaxies visible in our telescopes today would still be permanently unreachable. Not difficult to reach, not expensive to reach, impossible in the strictest sense that physics allows the word to be used. The space between us and them is growing faster than light could ever close the gap, even given the beginning of time itself as a head start. Think of the household budget metaphor for a moment, something almost embarrassingly domestic in scale. Imagine you owe a debt that grows by a fixed percentage every year, while your income only grows by a fixed, small amount every year. At first, your income might outpace the debt's growth, but because the debt grows by a percentage, a compounding rate, while your income grows by a flat number, there inevitably comes a point where the debt's growth overtakes your ability to keep pace, no matter how hard you work, no matter how much overtime you put in. This is precisely the mathematical shape of cosmic expansion versus the speed of light. Expansion compounds, light does not. Eventually, expansion always wins. And so we, standing on our small blue rock inside our modest town of a local group, are separated from the overwhelming majority of the universe, not by mere distance, but by a fundamental mismatch in the mathematics of growth. We built our entire self-image as a species, our myths of destiny among the stars, on an assumption of an open, waiting universe. The actual universe, it turns out, is closing doors behind our backs even as we speak. Now we descend into the mechanism itself, into the actual physics of what is happening, because understanding the anomaly requires understanding exactly where the assumption of infinite reachability breaks down. At the heart of everything is a boundary called the cosmological event horizon. This should not be confused with the event horizon of a black hole, though the two share an eerie family resemblance. A black hole's event horizon marks the point beyond which nothing, not even light, can escape the pull of gravity. The cosmological event horizon marks something almost like its mirror opposite, the point beyond which nothing, not even light, can ever reach us, because the space between us and that point is expanding too quickly. Here is the mechanism in its simplest form. Light travels at a fixed, unchangeable speed through space. But the space itself, the very fabric the light is traveling through, is expanding. For nearby galaxies, this expansion is slow enough that light easily outpaces it, and their light reaches us, red-shifted but intact. But beyond a certain distance, the expansion rate of the space between 2 points exceeds the speed of light. Past that distance, any photon emitted toward us today will never arrive. Not in a million years. Not in a trillion years. Not ever. The photon is, in a very real sense, running on a treadmill that stretches faster than it can run. The chilling part is this: galaxies do not vanish in a single dramatic instant when they cross this horizon. Instead, their light grows progressively more red-shifted, more stretched, more faint, approaching an asymptotic fade that never quite reaches true zero but becomes, for all practical purposes, undetectable. It is less like a door slamming shut and more like a voice calling to you from a train pulling away, audible, then muffled, then a whisper, then nothing, the silence arriving so gradually that you can never point to the exact moment it began. This is why astronomers describe some galaxies as frozen at the horizon. Their light appears to slow down, to stretch out over longer and longer wavelengths, becoming redder and redder, dimmer and dimmer, until it fades below any threshold our instruments, however advanced, could ever detect. From our perspective, we will never actually witness a galaxy cross the horizon in real time. We will only watch its light grow fainter and fainter across billions of years, an endless fade to black that technically never fully completes, yet practically erases the galaxy from our observable existence forever. Now overlay onto this the discovery that reshaped modern cosmology entirely. The expansion of the universe is not slowing down, as physicists long assumed it should, given the gravitational pull of all that mass tugging everything back together. It is accelerating. Something is pushing space apart faster and faster with each passing epoch. We named this mysterious pressure dark energy, a label that is, frankly, closer to a placeholder for our ignorance than a genuine explanation. We do not know what dark energy is. We only know its effects. A relentless, growing outward pressure baked into the very geometry of space itself, responsible for roughly 70% of the total energy content of the universe, dwarfing ordinary matter and even the mysterious dark matter that holds galaxies together. Because expansion is accelerating rather than merely continuing at a constant rate, the cosmological event horizon is not a fixed wall sitting quietly at some distant, unchanging boundary. It is contracting inward, relative to the number of galaxies we can theoretically ever reach or ever receive a signal from again. Every year that passes, more galaxies slip beyond the line from which their light could ever return to us. The observable universe, paradoxically, will continue to appear to grow slightly in the number of galaxies whose ancient light finally arrives after immense journeys. But the reachable universe, the portion we could ever theoretically send a signal to and receive a reply from, is shrinking, continuously, permanently, without any known mechanism that could ever reverse the process. Let us bring in one of the most unsettling instruments in modern astronomy to make this concrete: the James Webb Space Telescope. Webb was built to peer deeper into the past than any instrument before it, capturing light from galaxies so ancient that it left its source not long after the universe itself began, roughly 13.8 billion years ago. And Webb has done exactly this, revealing galaxies that formed far earlier, far faster, and far more massively than any existing model predicted. Astronomers half-jokingly began calling some of these discoveries universe breakers because they seemed to violate the very timeline cosmologists had built their careers around. How could galaxies this large, this structured, this mature have formed so quickly after the beginning of everything? But there is a darker irony hiding inside Webb's triumph. Every one of those extraordinary, universe-breaking galaxies that Webb detects is, by definition, already deep within, or in many cases already beyond, the practical reach of any future signal we could ever send. We are watching light that began its journey toward us billions of years ago, from galaxies that, if we tried to send a message back to them today, could never receive it, because the space between us has expanded so much in the intervening time that any outbound signal from us would never catch up to where they now are. Webb shows us the deep past of galaxies we can never speak to, a photograph of infants who have long since grown old, moved away, and vanished beyond any horizon we could ever cross to visit them. This is the deeper meaning of the phrase, the universe not being obligated to make sense to us. Webb hands us extraordinary, humbling images of ancient light, and each image is simultaneously a gift and a tombstone. A gift because it reveals a truth about the early universe far richer and stranger than expected. A tombstone because it confirms, image after image, that connection with that origin point is a one-way relationship. We receive, we can never respond. We are a civilization of eavesdroppers on conversations that ended before human beings existed, and we call it discovery. There is a second, smaller anomaly worth pausing on, precisely because its modesty makes the larger point sharper. Astronomers studying Neptune's atmosphere over recent decades observed something strange. Its clouds, once reasonably predictable in their appearance and disappearance tied to the planet's own seasonal cycle, largely vanished for an extended stretch of years, defying the models built to predict them, only to reappear later in patterns still not fully understood. On the surface, this seems like a footnote, a curious meteorological puzzle confined to a single planet on the edge of our own solar system. But it functions as a quiet parable for everything else we are discussing. Even within our own solar system, the tiniest, most intimately studied corner of the cosmos, the literal backyard of our species, nature still produces anomalies that our best models fail to predict. If Neptune's clouds, a mere few billion kilometers away, can defy expectation, what confidence should we truly hold about the sweeping galaxy-scale predictions we make about the invisible, untouchable expanse of a universe we can never physically visit? The lesson compounds. Our physics is extraordinary, our instruments miraculous, our models rigorous, and still, again and again, reality slips just slightly outside the frame we built for it. Multiply that humility across billions of light years, and you begin to understand exactly how tentative our grand narratives about cosmic expansion really are, even as their central, brutal conclusion, permanent isolation beyond the local group, remains stubbornly, consistently confirmed by every dataset we have gathered. So now we arrive at the spectrum of explanation, the range of hypotheses scientists have proposed to explain why the universe behaves this way, arranged from the conservative to the radical, each one carrying different implications for just how absolute, how eternal this coming isolation truly is. At the conservative end of the spectrum sits the simplest explanation: dark energy as a true cosmological constant, a fixed, unchanging property woven permanently into the fabric of space itself, first proposed in a rudimentary form by Einstein himself, though he later called its introduction his greatest blunder, only for later generations of cosmologists to resurrect it as perhaps the truest description of reality yet devised. Under this model, the acceleration we observe today will simply continue quietly, forever, at a fixed rate relative to the geometry of space. The event horizon will continue contracting steadily. Galaxies will continue crossing it one by one across eons of time, and the process will never reverse, never pause, never relent. This is, in a strange way, the boring hypothesis, and also the most terrifying, precisely because of how calmly inevitable it makes everything sound. No drama, no climax, no reversal, just an endless, patient erasure. Moving further along the spectrum, some cosmologists propose that dark energy is not constant at all, but dynamic, a quantity that could in principle change in strength or even in sign over cosmic time. This family of ideas is sometimes grouped under the term quintessence, models in which dark energy behaves more like a slowly evolving field than a fixed constant. If dark energy were to weaken over time, expansion might eventually slow, and the horizon might stop contracting, freezing the borders of our accessible universe rather than shrinking them further. Some more provocative variants even suggest scenarios in which dark energy might reverse polarity far in the future, from a rare theoretical family known as phantom or oscillating models, though most cosmologists treat these as speculative edges of the parameter space rather than favored outcomes, worth exploring but not yet supported by strong evidence. Recent observational campaigns studying vast numbers of distant supernovae and mapping the large-scale structure of galaxies across cosmic time have, intriguingly, produced hints, not proof, but hints, that dark energy's strength might not be perfectly constant after all, that it might have shifted subtly across billions of years of cosmic history. If confirmed by future generations of telescopes and surveys, this would represent one of the most significant revisions to cosmology in a century, potentially softening, though almost certainly not eliminating, the grim trajectory toward isolation we have been describing. At the more radical end of the spectrum lie the hypotheses that challenge the underlying framework itself. Some physicists propose that what we interpret as dark energy is not an actual energy or substance at all, but a symptom of our gravitational equations being incomplete, that Einstein's general relativity, magnificent as it is proven across a century of testing, may require modification on the largest cosmic scales in ways that would naturally produce the appearance of acceleration without requiring any mysterious new substance filling space. These modified gravity theories remain controversial, difficult to test, and so far unable to match the full weight of observational evidence as elegantly as the simpler dark energy models. But they remain live possibilities precisely because our understanding of gravity at truly cosmic scales is still, in an honest sense, a frontier rather than settled territory. An even more radical possibility, discussed more as a philosophical provocation than a mainstream prediction, involves questioning whether the acceleration we observe is a genuine physical effect at all, versus perhaps some subtle artifact of how we, sitting inside a particular possibly unusual region of the universe, interpret light traveling across vast, uneven cosmic structures. A small minority of researchers have explored whether we might occupy a special underdense region of the cosmos, and whether that local peculiarity could distort our measurements of an otherwise uniform expansion elsewhere. This hypothesis remains a minority position, generally not favored by the bulk of the evidence, but its mere existence within serious scientific discourse illustrates just how much remains genuinely uncertain beneath the confident language we often use to describe the cosmos. What unites every hypothesis along this entire spectrum, from the most conservative to the most radical, is a sobering shared conclusion. None of them, not even the most optimistic variants involving weakening dark energy, promise us a universe that remains permanently, fully open. At absolute best, in the most forgiving of the proposed models, the rate of isolation might slow, might stabilize, might leave us with a marginally larger reachable neighborhood than the bleakest constant dark energy scenario predicts. But in not a single serious evidence-supported model does the trend reverse entirely, restoring to us the vast, richly populated sky we currently observe. The overwhelming majority of galaxies visible tonight, in every serious framework currently taken seriously by working cosmologists, are destined to eventually fade beyond any horizon we or our descendants could ever cross. This is the strange gift and burden of science at its most honest. It does not promise us comfort. It offers instead a range of possible futures calibrated by evidence, none of which happen to include a version where the universe waits patiently for us to eventually catch up. We do not get to choose which hypothesis is true simply because one feels less lonely than another. We can only keep measuring, keep refining, keep watching the supernovae and the galaxy surveys for a sign that something, somewhere in the underlying nature of dark energy, deviates from the coldest, most conservative expectation. So far, the wall we described at the very beginning has not blinked. Let us now step back from equations and horizons and sit, for a moment, with what all of this actually means. Consider the astonishing coincidence of timing that has placed us exactly where we are. We exist during a cosmic epoch in which the sky is still populated, richly, generously populated, with galaxies whose light we can receive, whose structure we can study, whose history we can partially reconstruct. We are living, in a very real sense, during the golden window of cosmological observation, a window that will not remain open indefinitely. There was no golden window before us in any meaningful sense. The very early universe was too young, too dense, too opaque for the kind of grand-scale observation we take almost casually for granted. And there will be no golden window after us, at least not remotely comparable to what we possess now. Cosmologists studying the far future of the universe, projecting forward not merely millions but trillions of years, describe a moment sometimes called, with a certain grim poetry, the end of cosmology. In this envisioned future, so much time will have passed, and so much of the accelerating expansion will have unfolded, that the vast majority of galaxies currently visible to us will have faded entirely beyond the cosmological event horizon. Only our own local group, our own small town, merged by then into a single larger galaxy through the eventual collision with Andromeda, will remain visible in an otherwise perfectly, achingly empty sky. Imagine, if you can bear it, an intelligent civilization arising in that unimaginably distant future, evolving on some world within our merged galactic remnant, developing their own telescopes, their own physics, their own yearning curiosity about the cosmos. They will look up into a sky containing nothing but the stars of their own galaxy, no other galaxies, no cosmic microwave background radiation detectable in any meaningful sense, its signature stretched and diluted beyond recognition by that point. No supernovae flaring in distant clusters, no hint, anywhere in their sky, that an expanding universe of countless galaxies ever existed beyond their own shores. And here is the truly haunting part. Their science, if built with the same rigor, the same care, the same commitment to evidence that we hold today, will almost certainly conclude that their galaxy is the entire universe, not through arrogance, not through poor reasoning, through the simple, devastating fact that all the evidence available to them will point unmistakably in that direction. They will have no way of detecting a wider cosmos, no observational thread to pull that could ever lead them back to the truth of a Big Bang, an inflationary epoch, or a universe once brimming with billions of visible galaxies. Their physics will be internally consistent, rigorously tested, and quietly, profoundly wrong about the true scale of everything. Not because they failed as scientists, but because the universe itself will have erased the evidence they would have needed to know better. We, right now, in this fleeting cosmic instant, are the fortunate witnesses to a truth that will become permanently unknowable to every civilization that comes after us in our galactic lineage. We can see the expansion. We can measure the cosmic microwave background, that faint afterglow of the universe's infancy. We can watch ancient galaxies through instruments like Webb, tracing the shape of cosmic history back to nearly the beginning of time itself. Our distant descendants will inherit none of this. They will inherit only a beautiful, star-filled, utterly misleading sky, and the quiet, arrogant confidence that comes from mistaking the edge of what is visible for the edge of what exists. There is a strange responsibility hidden inside that realization. If the evidence for the wider universe is destined to disappear from the sky itself, then the only way that knowledge survives is if we choose to preserve it, not in starlight, but in memory, in language, in whatever record our civilization manages to carry forward across the abyss of time. We are not merely observers of the cosmos. We may be, without ever having asked for the role, the last generation capable of directly witnessing the scale of everything that exists, tasked with the strange burden of remembering on behalf of everyone who comes after us and will never get the chance to see it for themselves. And so we return to where we began, the wall in the sky, invisible, patient, tightening its grip one galaxy at a time. We are not explorers standing at the edge of an open frontier, free to venture outward whenever our ambition and our engineering finally align. We are residents of an island, watching the tide pull back farther every year, building rafts that will never be finished in time, sending letters to shores that will not exist by the time our words could ever arrive. The universe was never obligated to remain within our reach. It was never obligated to wait for us to grow clever enough, patient enough, technologically capable enough to cross its distances. It simply is what it is, vast beyond comprehension, expanding beyond negotiation, indifferent to the very existence of the minds now attempting to measure its edges. Perhaps the deepest lesson of the cosmological event horizon is not one of despair, but of perspective. That meaning was never meant to come from possessing the whole of the universe, only from the fact that, for this brief, fortunate moment in cosmic history, we were here at all, looking up, aware enough to ask the question, honest enough to accept an answer we did not choose and cannot change. Somewhere out there tonight, a galaxy's light is fading past the last threshold of our ability to ever detect it again. It does not announce its departure. It simply grows quieter and quieter, and then it is gone, folded permanently into a silence with no return address. We will never know its name. We will never know the exact moment it slipped away. And tomorrow night it will happen again, to another galaxy, and then another, in a rhythm indifferent to our attention, our instruments, or our grief. This is the shape of the wall we live inside. Not a boundary we approach and one day reach. A boundary that approaches us, patiently, silently, forever.